Hello friends. Welcome back. Today, we will continue learning about the PoligonSoft casting simulation system. This time, we will discuss mold filling with molten metal and the stresses that arise in the casting as it solidifies. We will learn how to properly set up the mold filling simulation, perform the calculation, and analyze the results. We will also calculate the residual stresses and deformations that occur in the casting immediately after solidification, as well as after the removal of the mold and gating system. Let's get started. I already have the master preprocessor open. Let's open the Sector A mod file. It's the same model we used in the previous lesson. You can download the file in the video comments. Since today we will see the stress calculation before and after removing the gating system, I divided our casting into several elements before the video lesson. If I go to the Start Simulation and Parameters menu, I can see that the rest of the parameters set in the previous class have not changed. We have defined an alloy temperature of 1580 degrees, and the mold and ambient temperature is 20 degrees. The material is GS45 steel, and we are using the sand mold template to set the mold materials and heat transfer parameters. Next, in the Solidification tab, we have fully defined the thermal calculation, meaning all the simulation parameters are set. We also have the porosity model activated, where macroporosity and microporosity are calculated. In general, that's it. Let's go to the Flow tab. Modeling the filling of the mold with the molten metal and other flow-related tasks are performed using the Euler solver. As a result of the calculation, the user can analyze the dynamics of filling the mold with the molten metal, see areas with incomplete filling, and also obtain the temperature fields of the casting and mold. The temperature fields at the moment when the mold filling is completed can be used as initial conditions for calculating the cooling of the mold. This, in some cases, significantly increases the accuracy of the results. Therefore, the filling calculation is performed before the solidification and porosity calculation. To begin, we need to enable the model. So let's check this box and see what other parameters are needed. The Save Simulation Time parameter activates an algorithm that calculates the minimum dimensions of the computational domain required to solve the flow problem. The computational mesh is constructed not according to the external dimensions of the model, but according to the dimensions of the casting with a small layer of the mold around it. Since during sand casting, the dimensions of the mold are much larger than the area of the mold that actually heats up during filling, enabling this parameter will allow us to significantly reduce the calculation time. The next parameter is the cell size. The flow calculation is performed using the finite difference method. In this method, the computational mesh consists of cells of the same size with a cube shape. The more cells there are, the more accurate the calculation will be, but at the same time, it will be more resource demanding and will take more time. The optimal cell size for a specific casting model can be determined as follows. We find the thinnest element in our model and measure its thickness. It is recommended that approximately 1 to 2 cells fit into the thinnest element. That is, in our case, we can set a cell size of 10 millimeters. The next line is the step for recording the results. Since filling is usually a fast process, a small result recording step is set here. Here we will set the value to 0.1 seconds. We will skip the initial mold temperature file, since this parameter is not necessary for sand casting. The adaptive correction parameter controls the internal correction algorithms of the solver. The auto value is suitable for most cases. However, when filling several molds simultaneously with a single gating system, it is better to choose the disabled value to obtain more realistic results. Next comes the current number. This parameter sets the time step for the calculation. If the current number is 1, the time step will be such that the molten metal will advance no more than 1 cell length in a step. With a value of 1, you will get very accurate results, but the calculation time will increase significantly. As practice has shown, acceptable results without a significant loss of accuracy can be obtained with parameter values around 5. We will leave the default value. The last line is the percentage of the solid phase, upon reaching which the flow of the molten metal stops. It regulates the moment when the molten metal can no longer flow because too much solid phase has formed. During mold filling, We not only calculate the flow process, but also the cooling process of the molten metal and the formation of the solid phase. A value of 0.5 means that in the nodes where 50% of the solid phase has formed, the flow will stop, and we will have incomplete filling. The best option to obtain the correct value for a specific alloy would be to build a 3D model of the fluidity test and adjust this number so that the fluidity simulation results match the data from the manuals. For our educational simulation, we will leave this value unchanged. For now, we'll stop here and close the window. Let's talk about how mold filling actually occurs in real life. We have some type of ladle, which can be a bottom pour ladle or a tilting ladle, from which the molten metal is poured. The molten metal reaches our mold in the form of a stream. It has certain dimensions, and there is even a place where this stream enters the casting mold cavity. To set the parameters of this molten metal stream, the inlets command is used. Let's start it. We see a dialog box. In PoligonSoft, almost any logic for pouring molten metal can be implemented. For example, we can pour most of the molten metal through the sprue and then fill the rest in the risers. Or simply pour the molten metal in several steps with pauses. To begin, let's click the New button to create a new process template. Below, we can enter the template name and a description. To create an inlet, we click the plus icon. This is what we see. Our inlet has been assigned index 1. The next column indicates the inlet's type. There are two types, molten metal inlet and molten metal outlet, meaning we can specify an area where the molten metal will exit the mold. Moving on to the next field, which is the stream diameter, and this is precisely the moment to visualize this stream. We select the location on the geometry where we want to create the inlet. Obviously, it's the sprue through which we pour. Press the Control key and left-click with the mouse. A circular geometric object is created. The circle has the diameter specified in this table, which is currently 60 millimeters. In our case, the diameter is larger than the channel itself, so let's reduce it to 40 millimeters. Next comes the metal pouring speed. And here, too, there are two options. We can enter either a constant value or a velocity curve as a function of time. It is assumed that when pouring molten metal from a tilting ladle, the velocity is approximately constant and is regulated by the inclination of the ladle. For bottom pour ladles, the velocity of the molten metal will depend on the level of metal in the ladle. The lower the metal level, the lower the velocity. Data on the flow velocity for most bottom pour ladles are in the database. For example, let's load one of the templates. We see that instead of a constant value, we have obtained a function that describes the dependence of flow velocity on time. If necessary, you can create your own function with the characteristics of the specific ladle and then save this data as a template for future use. To keep the lesson simple, let's use a tilting ladle with a constant flow velocity of 1.5 meters per second. I remove the loaded template, create a new inlet, and specify its parameters and location on the model. The flow velocity will be 1.5 meters per second. Then we need to indicate the start and end parameters of the operation. Let's suppose we want to pour the metal quickly up to 90% of the level, and then carefully fill it up to 100%. We set the end time of the first operation at 90%. Then we create a second operation using the plus button, again specifying a diameter of 40 and marking the entry point on the plane. The flow velocity will be 0.5 meter per second. The second step starts immediately after the previous operation with index 1 finishes, without delay. The termination criterion is filling the mold to 100%. All right, we have set the parameters for filling our mold. We click Apply and then Close. Everything is ready to perform the mold filling simulation. We can start it. We return to the Start Simulation tab. To speed up the calculation, I will disable the solidification and porosity simulation. We will calculate the entire complete process later along with the stresses. We start. We save our file and wait for the calculation to finish. Our calculation has finished. We run the Mirage post-processor to analyze the results. During the filling calculation, both the flow velocity fields and the temperature field of the molten metal are calculated. To see the temperature field, we will use the Open Temperatures button. The filling data is in the file with the prefix fill. It's important to clarify this, since if we had calculated not only the filling, but also the solidification, we would have a second file with the prefix solid. First, let's look at the color scale. In the first cell of the scale, the filling temperature is set, then in the next cell, the liquidus temperature, and in the last cell, the solidus temperature. The values in the remaining cells are evenly distributed between the liquidus and the solidus, so the colors of our scale correspond to the percentages of the liquid phase. If I press play, I will be able to see the filling process of our mold dynamically. If I'm interested in the temperature at a specific location, I can set a control point with a double left click of the mouse. To remove the points, I have to double right click the mouse. The visualization of the temperature field during filling is not the most informative tool. Basically, here we can only see filling defects, in cases where the metal cools down before the mold is filled in certain areas. This situation generally occurs when there are thin-walled elements or when the molten metal is not heated enough. We have a large part without small elements, so we will not have problems with misruns. Later on, we will use the temperature field as initial data for the calculation of solidification and porosity. In the previous lesson, we assumed that the temperature of the molten metal was uniform at the moment of starting the simulation. Now we will be able to obtain results that take into account that the temperature of the molten metal will be distributed non-uniformly, since during the filling process, different parts cool down at different rates, especially in areas where thin edges come into contact with the cold surface of our mold. Let's move on to the last step of the simulation. As we can see, the temperature at the edges is significantly lower than in the rest of the metal, and in some places, it almost reaches the solidus temperature. Similarly, we can see the velocity field. To see the velocity field, we select the third button that says Open Hydrodynamics. Again, we find the file with the prefix fill and open it. For a convenient analysis of the velocity field, we recommend manually adjusting the parameters of the color scale. Let's see how to do it. Here we have to advance the first steps up to this moment. Obviously, the maximum flow velocity will be here at the bottom. We can know its value. It turns out to be a velocity of around 3.5 meters per second. At the inlet, we had 1.5 meters per second. The stream accelerates rapidly as it falls. We can set the maximum value on this scale to 3 meters per second, a little lower than the measured value, since as the sprue fills up, the flow velocity will decrease. Let's set the lower value around 0. In our case, let's set it to approximately 0.1 meter per second. All values where the flow is slower will turn magenta. To distribute the values evenly between the upper and lower values, we uncheck the fixation checkboxes for all intermediate points and press Apply. We can review our simulation. Nothing out of the ordinary is observed here, except that the stream hits this place with a relatively high velocity, which can cause erosion. In a real case, it would be necessary to reduce the metal pouring speed or revise the gating system layout. If we advance to the end, we will be able to see the moment when the feeding velocity changes from 1.5 to 0.5 meter per second, as set in the simulation parameters. We will not dwell on a detailed analysis of mold filling, since everything here is very evident. If there is a lack of filling, our mold will not be completely filled. Primarily, the filling calculation is needed to determine the initial temperature field for the solidification calculation. Now let's move on to stress calculation. To calculate stresses, we need to have already calculated solidification. Certainly, we can start a general calculation, but in that case, we would be wasting time calculating the filling of the mold and solidification, and only then would the stress calculation begin. Since we have already calculated the filling of the mold with the molten metal, we can now calculate solidification and stresses separately, that is, as an addition to the previous calculation. We access the simulation settings again. First, we disable the filling calculation. We go to the Flow tab and uncheck the box. Now let's go to the Solidification tab and activate the calculation. We check the first box. Then, we increase the simulation step, since we don't need the same precision for stress calculation as for porosity calculation. We set a calculation step of 10 seconds and a step of 50 seconds for data recording. Furthermore, we will tell the program to use the initial temperature data at the end of the filling that we previously calculated. To do this, we check the box Use Initial Temperatures from Flow Results. With this box checked, the program will automatically search for the file with the prefix fill in the folder where our calculation is stored and extract the temperature data at the end of the filling. I can also manually specify specific files with temperature fields for the mold and the casting, but it is recommended to do this only when we want to use data from another simulation. For example, when we preheat the mold in an oven and separately calculate how much it will cool down while we prepare to pour the metal. To simply continue with the calculation performed earlier, it is not necessary to specify files. The program will detect them automatically. For stress calculation, we do not need porosity, so we disable the calculation of macroporosity and microporosity in the corresponding tab. Now let's go to the Stress tab. We check the first box Enable Stress Model to activate the solver. The next line sets the calculation step. Here you can put a large number, since the dynamic step is used in stress calculation. Let's set 100 seconds. The solver will automatically reduce the calculation step if it is not sufficient to obtain an accurate result, and if there are no discrepancies, the step will be increased again in the next iteration. This is very convenient because stress calculation requires a lot of resources, and by using a dynamic step, we can significantly reduce the calculation time. In the next line, we set the type of contact interaction with the mold. If I double-click on this line, I can choose from several options. We will select Rigid Mold. Not all molds can be considered absolutely rigid, but for educational purposes, this is the simplest model that does not require specifying additional parameters. This model assumes that the nodes of the mold mesh do not deform, and stresses in it are not calculated. This option is most suitable for sand casting. The automatic model fixation parameter is not required. It is only necessary for cases where our mold deforms or can break during the casting process, for example, in ceramic mold casting. Then we set the recording step. The data recording step can also be set quite large, because when we observe the stress pattern, we are generally not interested in the dynamics. We don't need to know how these stresses developed. Normally, we are only interested in the stresses in the last step. The next parameter is the threshold tensions. It is needed to reduce the file size. This is the stress value at which the recording of results should begin. For example, if during the first 10 seconds, the casting in the mold is in a liquid state, the stresses will be 0. There is no point in filling the file with those zeros. Here, you can set a value, let's say 5 megapascals, and when the minimum stress in the casting reaches 5 megapascals, the recording of results will begin. But in today's reality, with fast computers and large disks, this parameter can be considered obsolete. I don't use it. I will leave 0 here. In the previous lesson, it was established that the solidification calculation stops when the temperature of the casting reaches the temperature of complete solidification. But in reality, the casting continues to cool down, and when it reaches a certain temperature or after a certain time, it is removed from the mold. When it is removed from the mold, it can additionally deform because the restrictive influence of the mold disappears. Then, when the gating system is cut off, the casting is freed from the parts that could restrict it and deforms again. In the end, when the technologist analyzes the result, they take the already cooled casting with the cut-off gating systems and evaluate the dimensions and deformation of this piece. It turns out that in order to obtain the image that the technologist will finally see when inspecting the casting, we need to calculate the stresses not only until the moment when the piece solidifies, but beyond that, that is, until its complete cooling. It must be said that performing a calculation of the temperature fields and then a stress calculation, based on the temperature fields, until the complete cooling of the casting to ambient temperature, is not an easy task. The casting mold, by its characteristics, is almost like a thermos. It has a very low heat capacity and thermal conductivity. A massive casting cools for a long time and can take 1 or 2 days to cool down. If we try to perform such a calculation, setting the ambient temperature as the stop criterion, very large files will result, and their calculation will take a long time. To avoid performing the complete calculation, we can enable the parameter simulate stress after mold and gating system removal. With this parameter enabled, once the program runs out of data obtained from direct modeling, an extrapolation of temperatures will be made until the moment when all the nodes of the casting reach 20 degrees. Of course, extrapolation generates some error in the calculations, but it is much better than not calculating anything at all. Therefore, we can check this box. To increase accuracy, we can perform the calculation not up to the solidification temperature, but set a slightly lower temperature, around 500 degrees Celsius, which is quite feasible. Let's go back to the solidification tab. As a stop criterion, we select stop temperature and set a value of 500 degrees Celsius. We return to the stress tab. Then, we set the temperature at which the casting will be removed from the mold. Let's say it will be 200 degrees. And then, the temperature at which the gating system will be removed. It will be 20 degrees. Next, the order in which the elements of the gating system are removed is set. Here, separated by spaces, we enter the indices of the volumes of the elements that will be removed. If some elements have the same index, it is assumed that they are removed simultaneously. Volume indices 0 and 1 are ignored, so if you are calculating stresses, it is recommended to assign the casting the index 0 or 1. Let's see the values of our indices by double-clicking on the element we are interested in. Our gating system has index 2, and the additional gates have index 4. To indicate the removal order, in the field, we enter the index values separated by spaces. Suppose we first remove everything that corresponds to index 4, and then to 2. We enter the value for space 2. Next, we can save files with additional information, which can be very useful. By default, the results are recorded in a single file that contains information about stresses, strains, displacements, and cracks. That is, there are 4 fields. We can save additional fields that will be recorded in separate files. I am interested in the distribution of plastic strains, so I will enable it. If we don't know the tensile strength for the material and cannot directly predict the places of rupture, then we can evaluate the possibility of rupture based on plastic strains. If our metal has only undergone elastic deformations, they all cancel out when the loads are removed, that is, when it is extracted from the mold, and when the gating system is cut off. Plastic deformations accumulate. The places where we have the maximum plastic deformations are the probable places of rupture. All the criteria for hot cracks are based precisely on the analysis of plastic deformations or the rates of these deformations. That's why I included the recording of this field. Here you can also save the displacements in millimeters. Displacements are recorded in the main file, but they are recorded in meters. Since the displacements are really small, converting them from meters to millimeters is quite inconvenient. Also, from the interesting things here, you can, for example, save the separation between the casting and the mold in a separate file, if someone is interested in that. The hot crack indicator parameter includes recording the field of probability of hot crack formation. It is important to note that this hot crack prediction model is only applicable in mold casting processes. We will not do it in today's simulation. In addition to the main parameters, the stress model has many additional ones, and they are all available by pressing this button. Here we see several tabs that collect all the possible additional parameters that influence the work of the mathematical model, as well as additional parameters that will be of interest to the technologist. In the General tab, we see the damage criterion for the casting nodes, that is, the model that allows us to see in which areas cracks will form. By default, this model is disabled because it only works if we have the data that determine the dependence of the metal's tensile strength on temperature. Unfortunately, obtaining this data for a specific alloy is only possible through a series of experiments on quite specialized equipment. For the alloy we're using now, we don't have that data. We have reviewed all the basic parameters necessary to perform the stress calculation. Therefore, we close the window and click on Simulation to start the calculation. We click on Save and see that our calculation has begun. We continue after the simulation is complete. And well, we see that the calculation has finished. Now we can go to the Mirage post-processor and see the results. The results of the stress calculation can be loaded through the Open Deformations button. This command opens the main file in which, as I mentioned earlier, the fields of stresses, strains, displacements, and cracks are recorded. Here we see that we have 4 files. The first file with the prefix stress is the main file. The stress meldrem file shows the stress pattern after the mold is extracted. The stress rem4 file shows the stress pattern after removing the gates with index 4, that is, our channels, and correspondingly, rem2 after removing the sprue system. Let's open the main file and see what's in it. Since several fields are recorded in this file, the changes between them are made using the green buttons on the bottom panel. Here, by default, the D button is activated, which shows the strain field. The N button shows the stress fields. And then we have a button that activates the visualization of the displacement field. There is also a crack visualization and a scale factor, which I will talk about a little later. Let's review the stress field. First, I will go to the last step of the calculation, where a stress field already exists. At the beginning of the calculation, the stress field is 0. In the last step, I click on Uniform Scale to adjust the scale and obtain a certain stress distribution. I apply the parameters. What can we see here? The red areas are the zones of high stresses. We can adjust the scale a bit more by setting a different maximum value. For example, I can see that here the maximum value is around 900. I will take 950 and change it. Now I can see the areas with the maximum stresses. We should pay attention to these places. Despite the fact that the tensile strength of our alloy is 450 to 600 MPa, and it seems that the calculated values exceed this threshold. In our simulation, we assumed that we have an absolutely rigid mold, but in real life, this is not the case. If critical stresses arise, it is most likely that the sand mold will deform. It is important to remember that large numbers do not always guarantee a fracture, but they are only an indicator of places where problems may arise. To determine the fracture locations with certainty, it is necessary to also simulate the plastic deformations of the mold itself, in addition to establishing the characteristics of the dependence of the tensile strength on temperature. In this beginner's lesson, we will not cover that topic. It is not surprising that the maximum stresses occur in the gates, since the mold is rigid and the casting changes in size during the cooling process. It shrinks, since the sand prevents the free movement of the risers in the direction of the mold contraction. The maximum stresses arise precisely in them. Here, in the ribs, the situation is the same. The sand prevents the free sliding of this part, and a critical level of stresses also arises in this place. Now let's move on to the strain field. Let's adjust the scale and see how the zone of maximum strain looks. Again, I generate a distributed scale and raise the upper level a bit, like this. We see that the maximum strains coincide with the places where we observe the maximum stresses. Let's take a look at the displacement field. I switch to this mode and again set the scale. This scale shows the displacement of the mesh nodes from their initial position in meters. We see that the maximum displacement is in the center of the part, towards those parts of our casting that are fixed on all sides and cannot move anywhere. Here we see the modified geometry, that is, the distortion of the geometry. To better see the difference between what it was in the first step and what it became in the last, we can enable playback. You can see how the part and the gating system bend. In reality, according to the scale, the magnitudes are small, maximum around 2 millimeters, but visually we see the displacement. This is because there is a scale factor here. The scale factor is set with this green button. By default, it is 10. It can be made more or less. That is, if we look at it as it is, on a 1-to-1 scale, we will see little. This multiplier simply makes the image more illustrative. The last button is Show Cracks. In this case, it does not work. If it were enabled, the fracture locations would be shown with red dots. Now let's see how the picture changes after mold extraction and removal of the gating system. I will leave this post-processor on and run 3 more copies to see all the states simultaneously. I will open the stresses after mold extraction. We will compare the stresses. Let's set the maximum scale value for all values equal to the tensile strength of our alloy, approximately 600 megapascals. The first thing we see is that the stresses after mold extraction have significantly reduced, which is understandable since the mold no longer restricts our casting. This is especially noticeable in the areas where the mold joins the gating system. Also, the stress pattern has become more uniform. If at the moment of solidification, we have clearly expressed zones with low stress and clearly expressed zones with high stresses, then when extracted from the mold, we have a more uniform stress pattern. In fact, only noticeable stresses remain in the areas where these stresses are caused by an unbalanced change in the geometry of the part itself. Here we must take into account that the calculation of the stress field before mold extraction was performed at 500 degrees, and the calculation when we extracted the part from the mold was performed at 200 degrees. The plastic properties of the alloy change significantly at high temperatures. As a result, if we had stopped the calculation not at 500 degrees, but, for example, at the solidus temperature, the picture would be the opposite, since the stresses at temperatures above 1000 degrees will be significantly lower than when the part has already cooled down. The removal of the gating system did not significantly affect the pattern of our stresses. In our case, the removal of the gating system will not cause any additional problems. In the same way, we can analyze the strains and displacements, but in order not to make the video too long, we will not do it. The analysis is performed in exactly the same way as with the stresses. We switch to the desired mode, adjust the same scale, and compare. As for possible fractures, let's look at the additional field that we have recorded. The intensity of plastic strains. That is, only plastic strains, without the elastic component. We load additional data through the Open Universal File button. And here it is. We have 4 files with plastic strains. Since plastic strains accumulate, unlike the elastic component, we can directly see the level of plastic strain at the time of the last operation. I open the file for plastic strains after the removal of all elements. Here we see the following picture. These are the places where the plastic strains are greatest in this casting block. It is precisely by the plastic strains that we can assume that where they are maximum, there will be the highest probability of fracture. As we can see, the risk areas are the places where the feeders were previously attached. I would recommend completely changing the scheme of their connection. There are also problems with the upper rib, but as mentioned earlier, it is not a fact that problems will arise in this place, since it is more likely that the sand mold will break and not the part. In case the casting was not done in sand, but in a chill mold, close attention would need to be paid to this place. In the other parts of the casting, the plastic strains are low, and apparently, no fractures are expected here. With this, we end our lesson for today. Today we have learned to configure and analyze processes such as filling the mold with molten metal and the stresses that arise during its cooling. I hope this information has been useful to you. Have a good day, take care, see you later.